Hello, everyone. I'm going to start my lecture on queuing theory. What is queuing theory? Queuing theory is sort of mathematical work that deals with waiting lines. The queue. Queue is waiting line, and uh, we're going to construct the queue model to compute the queue length or waiting times. Like queue length means like you stand on the line and how long uh, the line will be, or how long you have to wait in the line. So mathematically we try to compute the queue length and the waiting time in the queue. Um, so the queuing theory has been considered as a part of the operations research, especially in the industrial engineering or telecommunication engineering. We are uh, you have to predict what happens in the queue, uh, and and uh, based upon this kind of models and computation, we're trying to make optimal decision about the resources that need to provide the service. This theory has been developed a I think the historically it's been quite long. I think early in 19th century, 20th centuries. Um, Actually, there was an engineer in Denmark named Lang. Lang was engineer who is working for the telephone company, and he actually came up with the idea of computing the call blocking rate based upon his mathematical model. And that was actually the first time we used the mathematics to predict the call blocking rate for the actual system, actual telephone system. And I think that's the first time one tried to use some sort of theory I mean the theory for the waiting time or blocking probability in the real system. So later in my course, I'll introduce what he has done in, in very old days, especially in his telephone system. Let me start with the basic model. Just assume that customers arrive to the service facility. Like, okay, you can imagine uh, customer comes to the bank, or uh, the patient arrive in the hospital or doctor's office, or car is coming to a gas station. Or you can think about a lot of different situation where customers, or even you can think about like telephone calls. You have switching system, and people make a phone call, and the call has to be processed in the switching system. And so from a switching system point of view, telephone call can be considered as customer. And or even in your computer, you have CPU, and CPU has to do a lot of jobs. And if you have multiple jobs coming in, the jobs has to be weighed in the queue buffer actually, right? Uh, so the buffer in your computer, or memory in your computer, uh, the jobs to arriving the job arriving the jobs arrived in the buffer can be considered a customer. So so all these customers arrive in the system, and then they have to be uh, weighted, right? Because I mean there's only one customer, maybe you don't need to wait. But if there are multiple customers already arrived in the system, they have to be queued up in the waiting room. And then the head of line, the one at the front of the queue will be served and then leave the system, right? And then next customer comes in and then serve it again and then depart, right? So this is, if you look at this, the figure, actually, we have arrivals. So customers arrives and there is a waiting room, which can represent the queue, which can be represented by queue, and then there's server, right? So anyone who is in the queue, okay, will be waiting, and then you, the head of line, you'll be next to be served, and then there, I mean, you have to spend some time to be served, right? The service takes time, so uh, so after certain service time, the customer will leave the system, and then there is another customer waiting in the queue will be served, and then leave the system again, right? So uh, the actually the your queue, okay, will depends on how many customers arriving and when they are arriving, and so mostly the thing is that the arrival will be random. So uh, our model, okay, our queue model very straightforward. This is a very simple model, and of course later on we'll discuss a little bit of a variation of this system, this model. For example, like we can have multiple queues. I mean, I'm sorry, not multiple queues, multiple servers, right? Server can be one or two or multiple of them, right? And also we have to worry about we have to worry about the queue size, okay, the waiting size. The waiting room can be finite or infinite. So like if it is finite, okay, there is like a maximum number of customers who can wait in the system, right? So if it is full, if this waiting room or queue is full, no one can, you can come in, right? So we have to worry about the size of the waiting room or queue size, right? So anyways, in this kind of queuing model, we have to there are many different characteristics we have to think about. One is arrival pattern, okay. Uh, like as I said, mostly arrival can be random, right? You don't know when the customer is coming in. Like if you think about the bank, okay, in bank you don't know when customer arrives, right? The customers come in at random times, or the customer can arrive like at with the period, like every 1 hour you can have one customer. Like if say this doctor's office, okay, your doctor is making reservation like every 30 minutes, then customers are arriving in 30 minutes, right? Every 30 minutes, right? So it's like deterministic arrival, right? So one characteristic you have to know about the system is, I mean, the model is arrival pattern. Okay, what is a pattern of arrival? And the second thing you have to think about is we have to know is service model, like how long it takes to serve each customer, right? And um, the service time itself can be deterministic or random, right? Like if you go to bank, okay, some customer actually spend more time with the teller than anybody else, right? Like say you open up the new checking account, okay, usually it takes time, or you just make a simple deposit, okay, then the service time is much shorter, right? So depending on type of service, the service time can be modeled by different service time can be modeled differently. Other thing is scheduling discipline. What I mean by the scheduling discipline is when you have a bunch of customers in the queue, um, of course, the most likely, the head of line, as I mentioned previously, okay, the one in front of the queue will be served first, right? Head of line customer will be served first, and then next one served, and so on, right? So there is always turn. Okay, you have to think about who will be served first, right? So like first come first serve is most fair way of serving the customers, right? But however, you can think about different disciplines, like last come first, first can be possible. In other words, the anyone who arrived the last can be served the first. Well, one simple example is that if imagine that the people in the elevator, right? People come to the okay. There are a bunch of people who come to elevator to take the elevator, and then like the one who arrived first will stand inside, and then one who last will stand in front. Then maybe the one in front will get out of the. I mean, they of course, okay, they wanna they want to get out of the elevator. The one who in front of the line will be the first one who's leaving the system, right? And so on. And then the one arrived at last will be I mean first. I'm sorry, the one who arrived first will leave the elevator last. So, or like you can serve. I mean, you can serve the customer at random, right? You just pick anyone in the queue at random and then serve, right? So there could be many different way of scheduling, okay, scheduling the service, right? I just mentioned the first come first served, last come first served, or random service, right? Random scheduling, right? And firstly, I have to worry about the queue size, right? The waiting room size. I call the system capacity. Actually, when I say system, okay, system include both server and the queue, right? If I can hold the K customers, okay, K customers, then system size, system capacity will be actually K plus one, because one, actually there is someone in the queue, someone is waiting in the queue, which implying that there is another customer who is under service, right? So the whole system, there will be actually K, the maximum number of the people we can have in the system is K in the queue and one in the server, right? Okay, server can hold one customer, right? So altogether, I have capacity of K plus one, right? Or okay, we have infinite size of queue, like the waiting room is huge. You can actually hold the infinite number of customers. The system capacity will be infinity, right? And the other feature, other characteristic for the queuing model would be like number of servers. Like you can have only one server or two server or multiple servers, right? If you go to bank, okay, there are usually, okay, the bank is large enough. It has multiple tellers. You usually see two or three or four tellers working together, and so one at the different windows, one at each window, right? So if you do have three tellers working at the same time, actually we have three servers, right? So each time, uh, each time, you know, at each instance, all three servers will be busy, serving individual customers. If we have a lot of customers waiting in the queue, right? Of course, okay, there is some idle time. If no one is waiting in the queue, then tellers, okay, the server might not doing anything, so must be idle, right? So so it really depends on how many customers arriving each moment. If you have a lot of customers arriving, so like arriving rate, okay, arrival rate, okay, the number of customers per second, okay, which is actually called the arrival rate. And if arrival rate is really high, you can guess that there will be a lot of customers waiting in the queue, and all the servers must be pretty busy, right? So for the rest of this lecture, I'll be looking at the different characteristics of uh, th- these items, like arrival pattern, service time, scheduling principle, capacity, and number of the servers. So uh, uh, depending on what kind of characteristics we have for the given queue, the actual waiting time of the queue, or queue length, okay, actual the length of the queue will be quite different, right? Or for example, like if you have a lot of servers, a lot of multiple servers, then waiting time will be much smaller than single server case, right? So we have to compute the uh, performance for the different characteristics. That's what we're gonna discuss for the rest of this lecture. I just mentioned the basic characteristics of queuing system, five different characteristics, and the first one is the arrival pattern. And the customers are actually coming from the certain population, and the population can be finite or infinite. And a lot of times in practice, we assume that population size is finite but very large, or like you can just say population size is almost infinity, right? If you have such an assumption, then the analysis can be very could be very easier. Um, it's going to give you a really good approximation to analyze the system. And so here, actually, this graph, this figure is telling you this the T's, Ti, T1, T2, and Ti minus 1, Ti. These are the arrival times. So um, like T1 will be the arrival time for the first customer, and T2 is arrival time for the customer number two. So Ti is representing the ith the arrival time for the ith customer, and between the arrival times, like between T1 and T2, actually you can define capital T2, and capital T2 is inter-arrival time for customer number two. So once customer number one arrived, you wait time T2, then second customer arrives, right? So T2 minus T1 is inter-arrival time for customer number two, and so on, right? So Ti is inter-arrival time for the customer number I, and this inter-arrival time can be fixed, like deterministic, right? You can predict when the customer is coming in, right? So if it's doctor's office, the if you have we have the appointment with all the patient, the arrival time will be actually predictable, and it's very deterministic, right? You exactly know when the patients are arriving. Or the inter-arrival time can be random, right? I mean, this is actually a typical situation, right? If it's post office, a bank, or like if you go back to my example for the computer jobs in CPU, the inter-arrival time will be random, right? Because you know when the job is arriving, right? It depends on the user, right? User actually do some work, depending on what kind of job you are casting. I mean depending on user behavior, depending on the type of job, the arrival time will be inter-arrival time will be random, right? Also, there's one story for customer arrival. Uh, the one actually a particular feature for the arrival pattern is like whether we have customer coming singly or coming in batches. What I mean by that is, okay, well, like if think about the bank, okay, the most of customers are coming alone, right? He or she is arriving to the customer to do something in the bank, and come singly, right, alone. Or like in a couple can come together in the bank, right? So it's kind of like it's batch of two customers. Or like uh, let's say there is a bus in front of the I mean there is bus stop in front of the bank, and the bus, okay, stops, and then many people, okay, taking off the bus will arrive to the system, arrive to the bank at the same time, or multiple customers arriving at the same time. So it's like a batch of the multiple customers, right? So in order to specify the arrival pattern, okay, you have to make sure that the customers are coming singly or coming in batches of a certain size. Anyways, in general, we have to we can define the inter-arrival time by the random variable, right? Mostly is random. So we have a certain distribution for the arrival time. So the distribution will be given in terms of a CDF of the T. It's now okay. The T so I. Okay, this is a into arrival time for ICE customer, and this random variable. Okay, and this random variable can be given by the CDF or its derivative PDF, right? So once you know the PDF of inter-arrival time, for example, you can find the average mean inter-arrival time, right? Mean inter-arrival time, right? Like this, right? Um, I have example, another example. Let's say that your arrival time, okay, is following the PDF like this. Okay, PDF is given by delta function, okay, which means inter-arrival time is always 1 over lambda, right? Okay, PDF is delta function, right? 1 over lambda. So in this case, okay, the inter-arrival time is deterministic, right? You have it deterministic inter-arrival time because always inter-arrival time is given by 1 over lambda, right? That's a very special case. Right? Okay, I have a little bit different story for the customer behavior. Okay. Once customers arrive in the system, okay, of course they have to wait in the queue first. Of course, if there is no one in front of you, you'll be immediately served, no waiting time, right? Otherwise you have to wait in the queue. And then let's imagine you're waiting in the queue, and I mean customers waiting in the queue, and see what happens. Okay, well, there will be many different behavior for the customer. One is like bulking. Bulking means well, okay, you arrived at the bank and you find that there are a lot of people already waiting in the queue. Then you're very discouraged, so you're reluctant to join the queue. So maybe you immediately leave the system without waiting in the queue. That's that particular behavior is called bulking. Lineaging is another different behavior. Okay, the customer joined the queue. Okay, I think this typo. There's a queue, but okay, he decided to wait in the queue, but while waiting in the queue, he find that the line is too long, so he may leave. Okay, he may leave the queue without until he or she is served. So at the middle of the queue, customer can leave the system, right? That kind of behavior is called lineaging. And one last behavior is jockeying. Jockeying is changing the line. Okay, when you have like different lines for the different teller, and the one line is much shorter than yours, then you decide to change the line, right? You actually move to different line for the different teller, right? But nowadays, okay, long time ago, I don't know, like. I remember that a long time ago, people we had multiple lines, one for each teller, right? So when you arrived at the bank, you look at the different lines, and then of course you're gonna join the shorter one, right? But nowadays we don't find any lines in the bank because there is a number ticketing, right? There is a service ticket. So you actually, as soon as you arrive in the bank, you get the ticket, and then you wait until your number is called. So we trying to have a single line. Everybody is waiting the single line, right? Even if we have multiple servers, multiple tellers. So the reason why we have a single line is if you follow the queuing theory, result of queuing theory, okay, it is good. It is better to have single line than multiple lines. Single line will give you better performance. Better performance means shorter waiting time or shorter lines, shorter queue lengths when you have multiple servers. Okay, that's the result of queuing theory. Okay, so the current banking system, okay, current operation in the bank most likely try to follow the nice result in the queuing theory, I think. Okay. Let's take a look at the second characteristics of queuing model, which is on service time. Let me use notation Z sub I uh, to represent the service time of the ith customer. Service time means how long it takes to serve the customer. If we look at this figure, okay, it's trying to tell you what's going on when a customer arrives in the system. This is typo, this is T sub I. T sub I is arrival time for the ICE customer, right? If he finds that server is busy serving somebody else in front of you, the arrived customer, okay, the one just arrived must be waiting in the queue. So there is a little bit of queuing delay that you have to experience. You have to wait in the queue, and then everybody in front of you leave the system. Your turn for the service. Okay, let me using the T sub I prime. Okay, this is time for your turn. Okay, server is starting serving you at this time. So this is the ICE customer service begins. This is time when service begins for you, and then there is service time, right? Which is Z sub I. After Z sub I, your service is done. Your job, I mean that the job has been done, and now you can leave the system. Service is done, right? Service ends, so you leave the system, right? So from here to here, this is time. This is service time, right? It's time when service starts and until the time until service ends. So in general, the service time is going to be random variable, right? So I have to use random variable to denote to represent the service time. And what will be the distribution of service time? And well, of course, you have to model. You have to model the service time, and in general, it's gonna be random, right? And the so unless it is deterministic, if it is deterministic, like okay, um, here I have some example like airtime flight, like older airplane and it's supposed to have the flight time. Usually it's fixed, right? It takes 10 hours to get to US, or like there's train travel time, is fixed, right? So like some cases the service time is fixed. It's fixed number, right? Deterministic. But mostly it's gonna be like random, right? If you go to post office, bank, um, or like in my early example under the operating system, the job, okay, to completing the job it takes time, but it takes random time depending on what kind of job it is, right? Also, if you go to bank, the service time depends on what kind of service you want, right? If you want to open up the new account, it usually takes time, so service time is tend to be much longer. And if you're just making deposit for the cash, maybe it's shorter, right? The service time is much shorter. So depending on type of, the service, the type of the jobs, the service time might be different. And we can ask some questions. First of all the customers supposed to have same type of service. It might be true or not, right? Sometimes you are okay. Even like if you okay, let me just use the same example for the bank. Okay, uh, when you open up the new account in the bank, okay, sometimes I mean it's not still deterministic because like say everybody in the customers are trying to open up the new account, but it might take different service time to for the different customers, right? Some people takes some people takes a little more time than somebody else, uh, right? It depends on situation, right? Depends on situation, depends on who you are. It might take longer or shorter, right? So, or if you want to make a deposit, still like depending on who you are, the service time might be varying, right? So, um, So we have different service time characteristics, service time model for the different job, right? Different type of service, might have different distribution, service time distribution, right? So that's what I mean by the service type. Okay, so in general, okay, customers might have the different customers might have the different service type. Some people, a group of people have one type of service, and the other group of people would have different type of service, and then those services will be mixed up. Uh, One other important question we might want to ask uh, is service time independent of each other? You have different customers, and let's. I'm still talking about. I'm talking about the same type of service. Okay, like opening up the new account, for example. And you have two customers, say customer number one and customer two, and both of them are trying to open up the new bank account. And my question is, okay, customer one, okay, the service time to open up the new bank account, okay, the service time for the customer one would be dependent on the service time for the customer two. And so in other words, service time of one customer will affect the service time of the other customer. So I'm asking the service time for the different users are dependent or independent of each other. And um, if you if you think about actual situation in the bank, okay, if you look at the two different customers, they are actually the customer itself are independent of each other. So even if they're trying to do the same job, like opening up the new account, the service time for the one user, one customer doesn't have to be dependent on what happens to the other customer, right? So I would say most likely it's independent, but some situation it will be dependent, okay? But it's a very exceptional case, okay? Most of the problems we're dealing with in queuing system, okay, we're assuming that the service times are independent of each other, okay? Service time of each customer, okay, will be independent of each other, and so this is the assumption we're gonna have. Um, Service time, okay, is this of i's. We have the service time are independent and IID identical. Okay, well, if I'm talking about same type of service, okay, same type, as long as the service type is same, they're gonna have identical distribution. Okay, this random variable is gonna have identical distribution, but okay, the random variable will be independent of each other. Okay, Z1 is independent of Z2. Okay, Z1 is service time for the the customer one, and Z2 is service time for the customer number two, and then they are going to be independent of each other, and they're gonna have same service time. They're gonna have same probability density function or CDF. Okay, so that's what I mean by the identical distribution and independent. So IID. Okay, so this is a typical assumption we're gonna have in most of the queuing models, queuing system. So service time is supposed to be IID. And let me use the notation B sub x to represent the distribution. This is CDF. CDF for the random variable z service time, and its PDF is I'm using the lowercase to denote its density. And the mean service time is of course given by this, right? And I'm using the 1 over mu to denote the mean service time. Remember 1 over lambda is mean, this is a mean arrival time, inter-arrival time, right? Inter-arrival time is 1 over lambda, and the service time is 1 over mu. Average service time is 1 over mu. So lambda and mu are two important notations we're using in queuing theory. Okay, I'm using these two notations on and on and on throughout my lecture to denote the inter-arrival time and the service time, right? Okay. At this moment, I like to discuss what we mean by lambda. Okay, 1 over lambda is inter-arrival time, right? So inter-arrival time is as time between two arrivals, and so this is okay. Maybe the unit. Okay, interval time unit is second, right? How many seconds it takes? Okay, between two different arrivals, and if that okay, I have okay this timeline time x. I have t1 and t2, and this interval time is actually uh, I can represent T2, right? T2 is interval time for the customer number 2, and average will be actually expected value of T2 is 1 over lambda, right? And what is lambda then? What is lambda? Okay, what is reciprocal of 1 of lambda interval? I mean, what is reciprocal of interval time? It's lambda is number of okay, there is only one arrival, right? There is only one arrival between the interval time. Within interval time there is only one. There's only one arrival, right? Okay. So then how many arrivals are you expecting on the average during 1 second? We're gonna have 1 over lambda, okay? 1 over lambda is interval time, then lambda is what? Lambda is going to tell you the number of customers per second, right? Right. There's one. There's one customer. One customer. It takes 1 of lambda. One of lambda. I'm sorry. This is 1 of lambda is actually second. Okay, it's number of second for one customer, right? In order to have one customer arriving, it takes 1 over lambda second, right? So lambda will be uh, the the number of customers arriving during 1 second, right? During 1 second, you're gonna have lambda customers. So lambda is kind of arrival rate, right? Number of customers per second. Okay, so a lot of times we are interested in we have to observing the arrival rate. Okay, every 1 second how many customers arriving. We can do the same thing for the 1 over mu. Okay, 1 over mu is actually service time, right? And what is mu then? Mu is going to be uh, the number of customers who finish the services in within second. Okay, every 1 second, how many customers will be served? That's actually service rate, right? Mu will be service rate, right? Number of customers who are going to be served during 1 second. That's service rate. So I'm using two notations, right? One for lambda, the other for mu, right? Lambda is for average arrival rate, mu is average service rate, right? And its reciprocal is actually interarrival time, and 1 over mu is service time, average service time, and average interarrival time, right? Okay. Now let me move on to the fourth characteristic, which is on the scheduling discipline, and I already talked about the first come first served and last come first served, right? Okay, depending on who comes first and who served the first. Okay, and this is really the first come first served is actually the fair discipline, right? Last come first served is not gonna be fair, right? But sometimes okay, we have to use this unfair discipline, last come first served. Also, there is a priority scheduling, which means like um, um, wait a second. I think I need. Okay, let me use slash here, and one is random. Okay, random service, which means you pick the customer at random. So you don't know who is gonna be picked up, right? So anyways, you pick anyone and then serve, right? Um, well, this is still sort of fair, right? But the one who arrived earlier will feel like it's not fair, right? Someone who came to the system last might be picked up first and then served, so that's not fair, right? And then there is one other important the scheduling discipline, which is priority scheduling, which means some customer might have priority than somebody else, everybody else. So the one who has really high priority will be served first. Okay, so like if there is a VIP customer, for example, okay, and this customer is really is a VIP, and so whenever you have a VIP customer, uh, this customer is not going to wait in the queue and served immediately, even if we have somebody else in the waiting in the queue. So this is very not fair. This is not fair at all. But sometimes this is going to be happen, right? You have to treat the high priority customer first, right? So this is one possible scheduling principle. Okay, and there's a term called there are two important terms related to the priority scheduling. One is preemptive, the term called preemptive. The other is called non-preemptive. And uh, I don't want to discuss these two the disciplines. As I said, these are both priority scheduling disciplines, and one is preemptive discipline, and the other is non-preemptive discipline. And I'll discuss these terms, these scheduling principles whenever necessary in the later in my lecture. Okay, I just talked about scheduling discipline, and that the next one is system capacity. Of course, okay, the system size can be finite, limited, or can be infinite. It's actually infinite size of system is unrealistic, right? Most of the real system has finite capacity, right? Uh, for example, like telephone system, we have finite number of the channels. Okay, so the number of the users um, speak, make phone calls will be limited. You can't have like infinite number of people can make a phone calls at the same time, right? Because we have a limited number of channels. Okay, so it's limited systems capacity. And also like if you look at the parking lot, okay, the parking lot, the size of parking lot cannot be infinite in reality, right? Always finite. So or like in queuing system, okay, you might have to specify actual size of the system, actual size of the waiting room. In other words, you have to specify how many customers can wait in the queue, or how many cars you can park into the parking lot. Okay, how many channels you have, right? These are kind of like real situation, right? You have finite number of channels, finite number of cars, a finite number of customers in the bank, and so on, right? So system capacity will be must be specified. And finally, you have to specify the number of servers, right? Mostly you're gonna have one or more, okay, servers. Um, so the number of the parallel server will be finite integer, right? The reason why it has to finite is like the minimum number of servers is one, or you can have two customers, I mean two servers, three servers, and so on, right? You have non-negative, I mean positive integers, right? The number of servers will be positive integers. And um, like if you think about the telephone system, okay, if you have like 100 channels, okay, then you have actually um, uh, if you do have 100 channels, okay, then you can actually you have 100 servers, but not only the number of channel itself is server, right? And also the whole system, okay, system has you have like 100 channels, like channel number one, channel number two, and you have channel 100, okay. And the customer arrives, I mean the calls, okay. Actually, I'm talking about the telephone system. So call arrives, and so uh, okay, if 100 calls arriving in the telephone system, okay, each of the call will be served by the individual channel, and of course, okay, the number of calls will be less than 100, but at most you're gonna have 100 calls, and the number of actually uh, the calls in the system will be the same as number of the channels you have, right? Because most likely, okay, your telephone call cannot be waiting in the queue. You know what I'm saying? All the call must be okay. You place a call, okay, and as long as channel is available, you immediately your call will be placed. And but however, okay, all the channels are busy. Okay, all the channels are used right now, and you place a call, then you're not allowed to make a phone calls, right? So maybe you hear busy signal, and then your call will be blocked immediately. So in that case, the number of channel will be same as number, in telephone system like this, the number of channel will be the same as number of uh, the capacity of the system, right? Okay. So I just described all five different characteristics of queuing model. Okay, as I have discussed different characteristics of queuing model, I'd like to introduce some notation to represent the structure of queuing system. What I mean by the representing the structure. We somehow, okay, when you given queuing model, somehow you must be able to specify what kind of characteristic it has. What I mean by the characteristic is all the characteristic I discussed of. We had the actual arrival pattern, and, service time, inter-arrival time, or systems, systems capacity, number of servers, all those things you have to specify, right? In order to make the specification easier, the Kendal has introduced very simple notation. So it's called the Kendal's notation, and Kendal's notation will tell you what kind of characteristics a queuing system has. So it's kind of like shorthand notation, okay? And this is what it looks like, okay? You're using A slash B slash X slash Y slash Z. Okay, actually you have five of them, okay? And the very first the very first one is telling you the interarrival time distribution, okay? The A over here is telling you um, the characteristic of arrival pattern. Okay, and arrival pattern will be specified by the interarrival time distribution. Remember, I'm using t or t sub I to represent the interarrival time, right? This is a random variable to represent the interarrival time, right? So the very first one is going to tell you, the very first notation over here is going to tell you um, distribution, okay, PDF or CDF of interarrival time. And the second notation over here, B, okay, the second notation will tell you the service time distribution. Again, okay, service time is also a random variable, so you need the distribution to specify it, right? And third notation is the number of servers. Okay, the X over here is going to tell you the number of the parallel servers, and Y, the first one, is tell you the system capacity, and the last one is going to tell you the scheduling discipline, like whether it is first come first served or last come first served, or priority scheduling, and so on. Okay, so you have to remember all these five different notation, and I'll give you the specific example in the following page. Okay, this is a Kendall's notation, right? That I just introduced, and I'll give you the specific example for this notation. For A is for interarrival time distribution, right? So what kind of distributions can we think about? Okay, there will be many different types of arrival, right? Depending on the specific, depending on the distribution of interarrival time. Okay, we're gonna have different notations for A. Um, okay, first of all, the simplest one is deterministic, right? If arrival time is deterministic, we're using notation D. Okay, the A can be D. Or interarrival time can be exponential distribution. Okay, you have exponential distribution for interarrival time. You using notation m for a will be used by the m. Or there is um, um, one particular distribution PDF given by this. This is so-called Erlang type K distribution. Okay, this particular uh, any random variable that follows this particular PDF is called the Erlang type K random variable, and this particular distribution has parameter K. Depending on K, you're gonna have different distribution, and this one has parameter lambda and K, right? Lambda is representing the actually average arrival rate. Okay, so in order to specify this particular distribution, interarrival time distribution, you have to tell what the lambda is, what the K is, right? Uh, so if k is equal to 1, using a notation e sub 1, k equal to 2, you use e sub 2. Okay, so e sub k, notation e sub k is telling you that the interarrival time is following the Erlang type k distribution. Okay, well, when k equal to 1, you substitute k with 1. Okay, well, okay, let's say k equal to 1 in this the PDF. Then you will immediately find out this distribution end up with this. Okay, this one reduces to the PDF like this, and this PDF actually corresponds to well-known exponential distribution, right? This is a PDF for exponential distribution, this exponential random variable, right? Okay, and the lambda is actually the average mean. Okay, the average of this PDF is actually 1 over lambda, right? And which is actually average interarrival time in this case, or lambda is average arrival rate. So if I give you the average arrival rate or average interarrival time, you know that the distribution of interarrival time for k equal to 1, right? By this exponential PDF. When k equal 2, distribution will be quite different from the exponential distribution, right? But still, you use this kind of like, to use this kind of generalized form of distribution, right? So by changing the value of k, you can describe many different types of interarrival patterns. Okay, so k equal to 1, so you're using E1, right? E1 is the notation for Erlang type 1, and most of the story in queuing theory, okay, we're dealing with exponential interarrival time. Okay, in other words, we are dealing with the k equal to 1 case. Interarrival time is given by the exponential distribution. So in that case, okay, E1, okay, we're using the different notation m. Okay, when I use the notation m for a, that's indicating that the interarrival time is exponential. Okay, so because that's most popular model in queuing theory. Okay, we're using spatial notation m. Okay, I'll tell you why. Okay, we're using m rather than some other alphabet. Okay, later I'll discuss it later. But the reason why we're using the character m is trying to denote the actual memory list. Actually, this m is trying to tell you is memory list. Okay, we trying to actually using m for the memory list. Okay, and why we using this particular situation memory list? Actually, exponential distribution. Okay, exponential PDF has the property called the memory list memories. Okay, exponential interarrival time has a memory list property. That's why we're using the character m to represent the exponential interarrival time. And we can also have some other distribution like hyper exponential distribution. We use HK, I mean XK, HK, and it again this is also has parameter K, and it's a little more complicated than the Erlang type K, but I'm just giving you the example as I'm giving you this one as an example. And sometimes arrival can be general. Okay, we don't there is no specific distribution. Okay, it can be any, it can follow any distribution. Okay, then we use notation G for A. Okay, so A can be E1, right? Or A can be when it is E1 is memoryless, I mean the exponential, right? Okay, or A can be E2. So when it is E2, you're using K equal 2 in this distribution, right? Um, or A can be G if arrival is general. Okay, if arrival pattern follows a general distribution, then use A equal to G. Okay. Okay. Now, okay, in the Kendall's notation, okay, second notation, okay, I have A slash B, right? B is the second notation in the Kendall's notation, and okay, B can be also deterministic. Okay, what is B? B is service time distribution, right? So service time distribution can be deterministic, right? Always you have the same unit of time to serve the customer. Or it could be exponential. When it is exponential, then we use the notation M again. Okay, M is for memoryless, right? Because exponential distribution is supposed to have a so-called memoryless property. So we're using notation M. And the service time can be also followed the Erlang type K distribution. So I can use E sub K for different values of K. And hyper exponential distribution, I can use HK, or it can be general, right? So the B can be G, okay? If B is G, then service time can be general, right? Right, third one is for, okay, I have a slash X. X is denoting the number of parallel servers, okay? How many parallel servers we have, okay? If I do have, if X equals 1, I have one server. X equal 2, I have two parallel servers. X equal 3, I have three parallel servers, and so on, right? Okay, so X can be is positive integers, right? And also y, okay, fourth notation over here, okay, fourth one is denoting the system capacity. So it tells you how many customers in the system, how many customers the system can hold in the system, right? So y can be one, is the one is actually you can have a maximum of one customer in the system. Okay, when I say system, it includes both servers and the waiting room, right? So you have a bunch of customers waiting in the system, the waiting room, and also you have a server, right? Server is also part of the system, right? So if you have like waiting room, okay, if your waiting room has size of 5, and you have two servers, then you have 7 customers you can have in the system, right? So you can have y equals 7, okay? So 7 is system size. 5 is waiting room size. 2 is number of servers. Altogether, you can have up to 7 customers in the system. So system capacity is 7, right? So I just talked about the y in the candles notation. And finally, I have z. The last one in the candles notation is denoting the scheduling discipline. So z can be first come first served, or z can be last come first served. Z can be priority, right? Or Z can be general. Okay, general discipline. Any discipline. Okay, so GD I use general discipline. Okay, so depending on what kind of scheduling discipline you have different Z, right? So now I just explained all about the candles notation, and I have specific example. The more specific examples here. Okay, you have a queuing system, and if y is infinity, okay, if y, what is y? Y is system size. You can have this is unusual, this is unrealistic, but theoretically you can have infinite size of capacity system, right? Infinite capacity, right? For the system, then y can be infinite, right? And then you can have um, first come first served queuing discipline, right? And arrival pattern. Let's say arrival pattern is exponential. Okay, so A is exponential. Okay, let me use. Okay, let's say A is exponential. So arrival pattern is exponential, and service time is exponential. Okay, and C. Okay, not C. X. Okay, let's say X is 1. Okay, one server there, and Y is equal to infinity. Okay, and Z is equal to first come first served. So I just specified 5 different characteristics, right? So I have okay, this is my Kendall's notation. E. Okay, well, I'm sorry. The when you have exponential, I use actually I use M, right? So I have M, right? So I have uh, m/m/1 infinity first come first served. This is Kendall's notation actually for this particular example. When I have exponential interarrival time, exponential service time, one server, infinite system size, and first come first served queuing discipline. I mean the scheduling discipline. So this is my notation for this particular example of particular queuing system, right? If I use, okay, yeah, say if I use 2 here, for example, okay, then I'm assuming that we have 2 servers in the system, this queuing model, the queuing system, okay, or I can use the you know last come first served different discipline. I can change all these notations for to describe the different situation, right? So I have to, okay, in order to describe the specific certain queuing system, I have to use five different notations, right? To describe each of these characteristics. But this kind of system, okay, m/m/1/ infinity slash first come first serve. This is so popular. This is so popular queuing system. So in this case, we actually skip the last 2. So I just use MM1. Okay, when I say MM1 queuing system, okay, it's implicitly telling you that I have infinite system size, and I'm using first come first serve that display. Okay, so MM1 is the one popular queuing system we'll discuss. Okay, and if I say DD1, okay, DD1 means interarrival time is deterministic, service time is deterministic, and one server. And this is really simple queuing system case, right? And also, if I do have GGCKGD, okay, well, okay, if I do have queuing system like this, okay, I have G. So G is for what? Interarrival time distribution, right? Interarrival time. So general arrival, and G for service time distribution, right? So I have general service time distribution, and C is the number of the servers, right? It's just C, any number, right? And K is finite system size, right? And GD, general discipline, right? So everything is just general, right? Okay, so it is a kind of like the most general queuing system, right? G can be anything, so any arrival pattern, any service time distribution, any number of the servers, any size of queuing system, any the scheduling discipline, So this is most general queuing system. This is the Kendall's notation for the most general queuing system, right? So for the rest of my lecture, I'll be I'll be analyzing the queuing system for special cases. For example, I'll be discussing MM1 queue. This is a very simple and special case, right? And also I'm going to discuss MMK. MMK means I'm going to have deal with the queuing system with the K servers, K parallel servers, and with the exponential interarrival time and exponential service time, right? And also later on, okay, I can also discuss MG1. MG1 means, okay, I have exponential interarrival time, but service time distribution can be general with one server only, right? So changing, okay, using this candles notation, okay, I can describe any type or any structure of a queuing system. Okay, so I hope that I have clearly introduced the candles notation, how we use it, and in the further development for the rest of the lecture. Okay, now let me start talking about some preliminaries we need to know for the queuing theory. And the first thing you need to know is Poisson process. Poisson process is most important random process that we need to employ in the queuing theory. And so this is something you must already know from your probability and random process class. Anyways, let me give you the brief review of definition of Poisson random process. And before we talk about its definition, you need to know that what it means by the independent increment. So let me give a definition: independent increment. Actually, I can give you example to discuss what I mean by independent increment. And let's assume, let me say, let me define x of t, random process x of t, which is trying to denote the number of arrivals during the interval between time 0 and time t. So actually, let me use the time reference t0, which is actually 0. So we always start from the time 0. And then if you have time t here, so we have interval time 0 and time t. During this interval, I have arrival at t1 and I have arrival at t2. So every time I have arrival, I have jump. So the x of t, trying to count the number of arrivals. So if you have two customers over here, you're gonna have two over here. And if you have one customer arriving at time t at t3, you have one here, right? So by time t, actually you have altogether you have three customers, right? Two at the time t1 and one at the time t2. So altogether, so x of t3, x of t is 3, right? During this time interval, you have 3 arrivals. So x of t is trying to denote the number of arrivals to the system during the interval between time 0 and time t. Okay, given this, okay, having said that, I can now define the the increment. What I mean by increment is, okay, every time, okay, you have jump here, you have jump at time t2, and you have the jump at the t1, so arrivals at the t1 and t2, and then and then at the beginning, actually, there is x of 0 is 0, right? Because from the beginning there's no arrival. You're assuming that there's no arrival at all. And as soon as you have arrival at the t1, there's a jump, right? That jump will give it increment, like from the 0 to 2. If you have two arrivals here, this is a batch arrival, right? Two customers coming at the same time. This batch. In previous pages, I told you that what I mean by the batch arrival. And anyways, so x of t1 minus x of t0, okay, will tell you how many new customers that have arrived during the interval between time 0 and time t1, right? So in this case, it's 2, right? So there was none at the beginning, and then at t1 you have two arrivals. So between time 0 and time t1, there are two arrivals. So the increment is 2. So this is increment, right? And between time t2 and time t1, actually I have additional increment over here, which is 1, right? So so during the interval, I can always count the new arrivals which correspond to the increment. And so here I have increment here, I have increment here, I have increment here. So this increment is x of t3 minus x of t2, right? So uh, uh, okay, now we know what I mean by the increment, and independent increment means all these increment here, increment here, increment here, all these increments are independent of each other. So the actually number of new arrivals is independent of how many arrivals you had previous interval. Then we are saying that the increments are independent of each other. So we have definition here. So I have a certain random process x of t, which is counting process, which what I mean by the counting process is, as I discussed in the example, it's going to count the number of arrivals between time 0 and time t, right? So I have a counting process x of t, and this counting process x of t is independent increment if all these increments are independent, well, from the beginning, okay, at the time t0 or time 0 you have no arrival at all, so none in the queue, and then as time goes on there will be increment, and all those increment independent. Okay, then this random discounting process is called is said independent increment. So in this case, in order to describe, in order to specify this counting random process, we only need to know the distribution of arbitrary increment. So as long as you know this this distribution, this probability. Okay, what is this probability? This is increment. This increment between time interval t and s, right? So as long as you know that the time the probability of increment for any interval, okay, any interval, okay, no matter what the interval is, if you know this probability, okay, then you know you know you know all about this particular random process, this counting random process. Okay, uh, and there is another definition which is about stationary independent increment. Okay, we have independent increment for random process, counting random process, and if this random process stationary, okay, well, we have random counting random process which is stationary and independent increment. Okay, well, what I mean by that is if the okay, you have increment, right? This is increment between two intervals, right? Okay, I have interval t and s. I have another interval t plus h and t plus s. I'm sorry, s plus. Uh, okay, let's say I have a interval t and s. I have another interval t plus h and s plus h. So I have, let's say, I have t and s. This is the interval, right? So, and I have another interval, t, h, and s plus h. This is another interval. So actually, this interval over here, actually, the length is same. Only difference is time shifted. So actually, the interval has been shifted by t, time t. If as long as if I do have the same distribution for the increment during this interval, and the the distribution of the increment in the shifted interval, as long as I have the same distribution. Okay, this is this is CDF for the increment in this interval, and this is CDF for this increment. If they have the same distribution, then which means distribution has not been changed, even if there is time shift for the increment, then we call this increment is called the stationary independent increment. So any independent increment which give you the same distribution after the time shift. Uh, it's called the stationary independent increment. Okay, now before I still didn't give you the definition of Poisson process yet, and before we go to the formal definition of Poisson process, we still like to understand the physical meaning behind the Poisson process, and let me give you some examples that we might come across with in our real life. Okay, I have a bunch of the random event. Okay, okay, let's think about you have a radioactive source, and it is emitting the alpha particles, and uh, so sometimes you might want to count the number of alpha particles during that has been emitted during certain interval, right? Which is obviously the number of alpha particles will be random, right? So like you have interval like T1 and T2, and how many alpha particles has been emitted during this interval. Okay, that's kind of um, that's random event, right? And also number of, the arrivals of customer due to the queuing system, like the bank. Okay, we have random arrivals in the bank, and you might want to count the number of arrivals during the certain interval, right? Number of customers arriving in this bank during between the time 9 o'clock in the morning and 10 o'clock in the morning, right? There's another random event, and also the you can think about car accidents. That you give an interval, you want to count the number of the car accident during the interval, and that will be also random too. And the breakdown of machine, which means okay, in the factory you have bunch of you have like hundred thousands of machines there, and some machines will break down, and you want to count the number of the machines that break down during the given interval. Also, like you have base station, and you want to count the number of phone calls, incoming phone calls, okay, to the base station, and you want to count the number of phone calls during the interval. And also you have internet router, and you want to count the number of packets. Okay, packets are coming into the router, IP packet coming, and you want to count the number of packets arriving the router during like 9 o'clock in the morning, and the 1 o'clock. I mean between 9 and 10 in the morning. Okay, something like this. So all these are the random event. And now okay, think about any random event, and then you want to count the number of the event occurring. Okay, so arrivals. Okay, arrival is event occurring during the interval. Okay, intervals between 0 and t. So you want to use the random variable n of t to denote the counting process. Okay, so again the n of t is counting the number of the events, random events occurring between time 0 and time t. And here, okay, the counting process is discrete. Okay, well actually, uh, if t is fixed, if t is fixed, it's random process. Okay, counting process is random process, right? T can be any. Okay, but given t, fixed t is kind of a random variable, right? For fixed t, you have the total number of the event that occurred. And let me denote the probability. Okay, probability of this random process n is equal to n uh, p sub n of t. So this is what this is PDF at time t. So if I fix time t, it's kind of PDF, right? So this is PDF at time t, and this is actually probability mass function, right? Because n is discrete, so rather than using term PDF, I would like to use the probability mass function, and so there's a probability that the event occurred is n. right, at time t, and of course this distribution, this probability mass function changed by time t. So you might have different number of arrivals, okay, in 9 o'clock in the morning and one in the afternoon. So time by time, the distribution might be changed. So you have the different um, behavior in the system. And so far, I've been talking about, like, I've been using the counting process. Okay, counting process is the one like this. Okay, there's, like, jump, right? There's a jump here. So I have T1, T2, T3. Discrete time, I have jump, right? And as I said, this is a counting process. This is a counting process, and that I have increment, right? Actually, increment size is 1 in this case, in this example, and if uh, 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 okay, well, here I'm using the only one arrival at each event, right? Every event occurred, then I have one increment. But I can think about some other process, counting process, which give you the different number of arrivals, right? You have T1, you have one arrivals. T2, you have two events occurred, two arrivals. You have two here, right? The increment is 2 here, right? And T3, you have actually increment 1. T4, you have increment is 2 here, right? So 1, there's 2, 1, 2, 1, 2, right? So you can think about all different kinds of, the counting process. But among all these counting process, Poisson process is one most popular one. Actually, what I mean by that is Poisson process also counting process. Okay, but it's a very special case of counting process. So, uh, okay, well, okay, all of the examples I described here, most of the examples over here actually can be modeled by the Poisson process. And can you think about any common fact among all these examples? Um, like the number of customers arriving in the bank, or number of number of accident occurred during the certain interval, or number of phone calls to the base station during certain interval. What would be the common factor behind these events? Well, uh, okay, well, from our experience, okay, from our daily life experience, okay, we have, okay, of course, we are all these arrivals are random, okay, but uh, there might be some other common observation in this event, and let me discuss it in the following page. Okay, I like to define Poisson process. There will be two different definitions. Maybe one will be very formal one. Then later on, I'll give you a very rough definition based upon a physical meaning of Poisson process. In order to define Poisson process, okay, Poisson process is also random process, and which is actually counting process. Um, is a counting process, and if you might remember the definition of Poisson random variable, okay, if you do have a random variable x, and if the random variable x has the following uh, probability mass function with the parameter alpha. Actually, alpha is known as mean of Poisson random variable, and so as long as a certain random variable has the following probability mass function with the parameter alpha, we call that random variable Poisson. And one interesting fact about the Poisson random variable is it has I mean, its mean and variance are same. Okay, the variance of random variable, the Poisson random variable x is, say, alpha. Okay, then its mean is also alpha. Okay, And if you use notation sigma square for variance, the mean will be sigma square too. Okay, mean and variance are equal to each other. Well, okay, if I go back to definition of formal definition of Poisson process, it's, as I said, it's counting process N of t, and definition N of t is number of arrivals by time t. Okay, starting from time 0, and you have time t, and between time 0 and time t, the number of arrivals, okay, will be denoted by the N of t, and this is counting process. And uh, if n of t has it has parameter lambda, which is actual mean rate. Okay, its unit will be number of arrivals per second. Okay, so this is the mean arrival rate, lambda. And so if this counting process has following two, it satisfies following two things. We call this particular counting process as Poisson random process. And these two conditions include okay, the first condition is saying that the process has stationary independent increment. Actually, I defined what I mean by independent increment, and I also define what I mean by the stationary. So the counting process must be stationary and independent increment. And second of all, uh, the increment, actually this is increment, nt minus ns increment. Actually, you have time s and time t, and the difference is nt minus ns is actually number of arrivals between time s and time t, right? By time s, you have n of s arrivals. So by at time n and time s, you have n of s arrivals, and time nt, you have nt n of t number of arrivals altogether, and so number of arrivals between s and t will be nt minus ns. That's the increment between time s and t. So the distribution of this increment will be following the Poisson distribution. Okay, Poisson distribution given by this Probability mass function. So actually, the k here will be increment, and as I said, the increment is supposed to follow the Poisson distribution. So Poisson distribution is supposed to have a parameter uh, alpha, right? The alpha over here, it will be actually lambda times t minus L. Actually, the alpha is mean, right? Mean of increment is uh, lambda times t minus s. T minus s actually this the interval we're looking at. Okay, so we have alpha here. We have so alpha to the k's power divided by k factorial times e to the minus alpha. This is alpha, right? Okay, so as long as alpha is lambda times t minus s, okay, then this increment will be the so the increment, as long as this increment is following the Poisson distribution, the process n of t will be Poisson random process. And by the by the nature of Poisson distribution, the mean, okay, mean and variance of the increment will be the same. So in summary, Poisson process is counting process with uh, is counting process with the Poisson distribution with the parameter lambda parameter given by the lambda times t minus s. Okay, so having said that, now I'd like to look at the different nature of this arrival process, the Poisson process. Okay, let's take a look at the interarrival times. We have defined the interarrival times. Okay, starting from the t0, and then every time you have one arrival. Okay, t2 you have arrival, t3. So I'm marking. Okay, so I have arrivals here, arrivals. Okay, and interarrival time is of course defined by the time between two different arrivals, right? So starting from 0 to first, okay, arrival, I have interarrival time t1, and first to second arrival I have interarrival time t2 and t3 and so on. And of course, okay, these interarrival times suppose random variables, right? Because arrivals are random. And so I have defined the interarrival times, and now my question is, what is the distribution of interarrival times? Okay, actually, interarrival times are random variables, so it's supposed to, okay, we need to specify each distribution, right? And my conclusion is, if the arrivals are Poisson process, if we do have Poisson arrivals, then interarrival times are supposed to follow the exponential distribution. Okay, so I'll try to prove that interarrival times are following the exponential distribution in the following pages. Okay, in the previous. Okay, now I'd like to give you different different way of defining the Poisson random process. Earlier, I gave you the more formal definition of the Poisson process, and now the one I like to give you, the definition I like to give it to you is based upon the physical observation. So I would say it's a physical model-based definition. Okay, so let's say, okay, you have a Poisson rival process. I mean, you have just a rival process N of t, and if the following two assumptions are satisfied, I would say any rival process that satisfies these two assumptions will be Poisson process. Okay. So first of all, let me discuss what these assumptions are. First of all, the number of arrivals over non-overlapping intervals is independent, which means, okay, in time interval you have, say, t1 and t2, and you have another interval t3 and t4. So let's say you have two intervals. Okay, intervals. Okay, between t1 and t2, and another interval t1 and t4, and as long as these two intervals are not overlapped, then the number of arrivals, okay, the number of arrivals in each interval, okay, will be independent of each other. Okay, so here the number of the increment between T2 and T1, and this is increment between T1 and T2, and this is increment between T3, right? Okay, so okay, the increment will be the Poisson random process, and these two Poisson random process, okay, will be independent of each other. Okay, that's what this first assumption says. And second assumption is there is no rush hour. Okay, what do I mean by the rush hour? Rush hour is like given uh, during very short time. Okay, there will be like bunch of arrivals at the same time. Okay, so you have, like, okay, in time axis you have t, and you have you have t and t plus. You have t. You have t and t plus delta t. Okay, you have short interval, very short interval delta of t, and there will be bunch of arrivals here during this short time period. And then this is rush hour, right? Like a lot of arrivals during very short time. That's rush hour, right? But it says there is no rush hour. That means there is no bunch of arrivals during the short period. So that means, okay, that implies that arrivals is supposed to be single. Okay, what it means by that is during very short interval delta of t. Okay, if delta of t is very small, let's say delta t goes 0, okay, very small, then there is only if there is arrival, okay, it's going to be only one arrival. Okay, there would be, okay, so there are two possible events. One is there is no arrival between, I mean, during this delta of t, or there is only one arrival during delta of t, during delta t. Okay, or okay, in other words, there is no, okay, there is no more than one arrivals during this short period of time. Okay. Okay, so that's what it meant. Okay, well, mathematically, this is what it says. Okay, there is okay, this is an interval, right? You have t and t plus delta t. This during period of delta t, probability of one arrival, right, is given by this. Okay, there is, okay, well, as I said, there is only one arrival, right? So, okay, let me tell you what, okay, why this probability? Okay, what is probability of only one arrival during this interval? Okay, actually, okay, um, if you find, okay, let's take a look at the average number of arrivals during this short period of time. Okay, how do you find average? Average is actually okay, okay, sum over, okay, so like zero arrival times probability of zero arrival during delta t, and plus 1 times probability of one arrival over delta t, plus 2 times probability of two arrivals over to delta t, and so on, right? This is all average, right? This is what this equation trying to tell you. Okay, the thing is, there will be only one arrival. Okay, there won't be no more than one arrival during this short period of time. So actually, this probability over here, okay, there is no two arrivals. Actually, there is no, okay, there's 3 times probability of 3 arrivals during delta t, and this is going to be 0. Okay, only, okay, either 0 or only 1 arrivals. This is what it means. So if 0 times this one is 0, so 0. So you only end up with this, right? And what is, okay, now the question is, what is okay, so what is the average number of arrivals during this period? The short period is same as probability of one arrival in this interval, right? And what is so what is this probability? Actually, the what is the average number of arrivals over delta t? Actually, that's lambda times delta t, right? Actually, lambda times t is the number of arrivals, average number of arrivals during from time 0 to time t, right? Okay, so during time delta t, we want to have lambda times delta t arrivals on the average, right? Okay, now this is going to be approximate actually. Why? Actually, it depends on delta of t. It depends on, okay, delta of t is supposed to be very short period. If delta t is not short enough, there might be more than one arrivals, right? So we have to make sure the delta t is small enough, right? But we don't know how small the delta t is supposed to be. So actually this probability over the average number actually is going to be equal to, okay, well, I would say this is actually approximately lambda delta t, approximately lambda times delta t. But if you want to make it equal, okay, if you want to make it equal to each other, then I need some correction factor. This is, okay, this is a notation. Okay, actually I'm trying to define notation over here. This notation is trying to tell you, okay, some okay, well, actually it's going to be a very small number. Okay, this is a very small number for correction, okay, to make it equal. And this, okay, I'll call it little o of delta t, and this is a positive number which is smaller than delta t. Okay, so which means if you look at the ratio of little o of delta t and delta t, okay, this one goes to 0. When delta t goes to 0, this one goes to 0. Okay, which means little, okay, in order to, okay, this is true. This is true. This is true only when little of delta t is smaller than delta t, right? So delta t goes 0, like, little of delta t goes 0 faster than delta t, right? So this is what it means. So in other words, when delta t goes to I mean, if delta t is getting smaller and smaller, little o, okay, will go to zero, right? If delta t goes zero, okay, which means the interval, okay, interval, this short interval, the rush hour, okay, rush hour is, I mean the not rush hour, the short period of time, okay, is smaller and smaller, then this one goes to zero, so maybe it goes to equal, okay. Now you will have this probability equal to lambda delta t, but okay, when delta t is not small enough, okay, this is not going to be zero, so you need this whatever this value is, you need this one to make it equal to each other, right? So my conclusion is, okay, the average number of the arrivals, okay, is same as the one arrival in this interval delta t, and which is equal to lambda delta t. Okay, so that's why, okay, one arrival, probability of one arrival in this interval, okay, short interval, is this probability is lambda times delta t plus little o of delta t. Okay, now one other question is, okay, well, okay, we have three possible events, right? No arrivals, one arrival, or more than two arrivals, right? But however, we're saying that, okay, delta t is small enough, okay, this is not going to happen, either no arrival or one arrival, right? Only two events. So if that's the case, okay, what is probability that more than one arrival in this interval? Okay, so more than one arrival means actually two or three or more, right? So actually 1 minus this probability, okay, this is probability of one arrival, right? So 1 minus this probability will be actually probability that more than one arrival in this interval, right? So 1 minus lambda delta t plus little of delta t, right? Okay, this is actually 1 minus lambda delta t minus little of delta t. Okay, well, now you have actually, okay, 1 minus lambda delta t over here, and then minus 1 minus little of delta t, right? Actually, it doesn't matter whether I put a minus or plus. This is correction factor, right? This one goes to zero anyways when delta t goes zero. So this one is going to be zero anyways. Okay, so this quantity, okay, this quantity is just symbolic. It's symbolic in the sense that, okay, we can just ignore as long as delta t is small enough. So it doesn't matter whether it's plus or minus. Okay, that's why I'm adding plus sign over here. Okay, so I just discussed two assumptions behind the physical model. Okay, so let me summarize again. Okay, this the number of arrivals will be independent as long as the intervals. Okay, if the number of arrivals over non-overlapping intervals, okay, will be independent. That's the first one. And the second assumption is if you have a short period of time, the number of arrivals will be either 0 or 1. Okay, you're not gonna have more than one arrivals. Okay, and one thing you should remember is the number of arrivals. I mean, number of the one arrival in this interval is lambda times delta t, approximately, and or lambda plus delta t plus little of delta t, right? Okay. So as long as these two assumptions A and B, okay, these assumptions, I mean, as long as these assumptions satisfied, okay, actually assumptions 1 and 2, right? Not A and B. Actually, assumption 1 and assumption 2. Assumption 1 over here, assumption number 2. Okay, these assumptions satisfied, then the arrival process N of t is supposed to be Poisson process with mean arrival rate lambda. Well, actually, when I say mean arrival rate, mean rate is going to be lambda, I think. Okay, lambda is the rate means it's arrivals per second, right? Arrivals per second. Okay, so if you multiply lambda times t, okay, t is the interval, right? So actually, so lambda times t will be the total number of arrivals during the interval, right? So depending on the context, mean rate, okay, can be the lambda. Okay, so I think the lambda is more appropriate because rate means, okay, number of arrivals per second. So I think when you say mean rate, it gotta be lambda rather than lambda t. Okay, but sometimes, like, Poisson process, okay, the parameter is alpha is lambda times t, right? So sometimes we call this alpha as a rate. Okay, so depending on context, okay, we're using different meaning. So, but I think the okay, mean rate of lambda will be more appropriate, I think. Okay. Okay. Well, in this page, we want to actually prove that the prove that if the two assumptions we just discussed, I think that's assumption number one and assumption two, as long as those two assumptions satisfied, then I'd like to prove that the N of t is Poisson process with the mean arrival rate of lambda. Okay, so uh, okay, so the physical based model, okay, I mean the physical model based definition. Uh, so I gave you the physical assumptions, right? And we want to check if any process that satisfy those two physical assumptions supposed to be a Poisson process. And how do you prove it? In order to prove that, actually you have to show that show this, right? What is this? Pn of t is what? Piece of n of t is actually a number of arrivals. Is probability that number of arrival will be n by time t. So you have time 0, you have time t, and in this interval you're supposed to have actually n arrivals. Okay, the interval of time t, I mean the interval over time 0 to t, uh, the probability that you have n arrivals, so Pn of t, right? Okay, it's supposed to be lambda t of n factorial over e to the minus lambda t. If this is true, okay, if this is true, then n of t is Poisson random process, right? So you want to show that you want to drive this based upon the two assumptions I just discussed. Okay, so we need to show this. In order to derive this, we are going to derive the differential equation for piece of n of t. Okay, I'm going to set up the differential equation for this probability. Okay, and let me actually look at two different cases. One is n is greater than or equal to 1. So n is actually, okay, more than actually 1. More than 1. So 1 arrival or 2 arrival or 3 arrivals and so on, right? So, or the second case is going to be, so I'm going to take two cases when n is greater than or equal to 1. Second case is when n is equal to 0. So which is actually no arrival case, right? N equals 0 means there is no arrival. Okay. Now let's take a look at this interval piece of n of okay. I have time t. No, I'm 0, and then I have time t here. I have delta t plus delta t plus delta t. I have two intervals actually here. Okay, well, actually, this probability over here is actually looking at the number of arrivals from 0 to t plus delta t, right? So how many? Okay, well, n arrivals in this interval. Okay, you're looking for this probability, and actually, I can split this interval in two different intervals, right? 0 to t and t to t plus delta t. I have two intervals here. One interval here, another interval here. And we can see these two intervals are non-overlapping, right? Okay. So actually, total number of arrival over this interval will be actually number of arrival in this first interval here and the number of arrivals over here. So if I add, okay, number of arrivals in each interval will be total number of arrivals in, over the whole interval, right? So So I'm okay. I want to make sure that okay, we want to have n arrivals during this interval, right? N arrivals over this interval, the whole interval t plus. I mean, until t plus delta t. And think about how many different cases. Okay, well, if you don't have any, if you don't have no, I mean if you don't have any rival in the first interval, you gotta have n rival during this over delta t, right? Or actually, if you do have one arrival over here, you're supposed to n minus one over here. Okay, but if you do have two over here, n minus two, then you're gonna have total of n, right? But if delta t over here, the interval delta t, okay, this delta t is really small, then our one of the the physical assumption we discussed is over delta t, we're not going to have more than one arrivals. So the maximum you can have is one, right? So actually only two cases. I would have none arrivals, no arrival during delta t, or one arrival. Okay, I'm not going to have three arrivals. I'm not going to have four arrivals, right? Because of the assumption we made. So if I do have zero arrival in this interval, okay, then I must have n arrival over zero to interval of 0 to t. If I do have zero arrival over delta t, then I need to have n minus 1, right? So that I can have a total of n arrivals over the whole interval, right? I only have two events, right? So these are the only two events I have, right? Okay, actually k equals 0 and k equals 1. K equals, this is k equal to 0 case, this is k equal to 1. Okay, so k equals 0 is actually, k is the number of arrival over delta t over here. Okay, so you can think about these lines, and actually I have two terms, right? So in order to have n arrivals over whole interval, actually okay will be given by this, right? So this is what it is. Actually, if you write it out, okay, you have m minus 1 arrival by t times probability of uh, uh, one arrival over delta t, right? This is my shorthand notation, okay? Plus p m of t, which means I have n arrival over time by time t times probability of actually no arrival over delta t, right? So this is the summation is actually, if it's write out the summation, this is what it is. Okay. So now I have I have equation here. Okay, this probability is equal to, well, this I have written. Okay, this one times this one. Okay, on n arrivals, probability of n arrivals over this first interval times no arrival over delta t, and p n minus 1 arrivals over in the first interval, and then over during short period of time I have one arrival, right? And then actually I need to have this correction factor, right? Correction factor, right? Why do I have correction factor? Okay, correction factor, right? Why do I need a correction factor? Because this equation, okay, is actually approximation, right? If you want to make it equal, I mean, why is it approximation? Because it depends on how small the delta is, right? The smaller the delta is, it's gonna be accurate. Okay, so in order to make it equal to each other, okay, the left hand side and the right hand side to be equal to each other, you need some correction factor, which is little o of delta t, and this one goes to 0 when delta t goes 0, right? So now I have equation like this, right? Okay, what is, okay, first of all, well, what is the probability that there is no arrival? Actually, this is what it is. We have seen this in the previous page, right? And one arrival in the interval, okay, this is the one, right? Okay, so I have the whole equation here, and you rearrange the terms. Okay, you rearrange all the terms. You get this equation. You get this equation. Okay, so you have to rearrange the terms like this. And then the next thing is you divide on both sides. You have delta t here, delta t here. Okay, so you divide both sides. You divide both sides by delta t. So this is what I'm going to do. I'm going to divide by delta t. So I don't need this. I need this, and then divided by delta t, divided by delta t, divided by delta t, and then let delta t goes to 0. Okay, then what happens? This one is actually derivative, right? Derivative with respect to t. Okay, and literal of delta t now is delta t. Literal of divided by delta t, literal divided by all these go to 0, right? Going to 0. So I'm going to end up with these two terms. Okay, which is one over here. So I have now I now have differential equation. Okay. So I have differential equation here. Okay, if you solve this differential equation, you're gonna end up with the Pn of t. Okay, and then if you show that this solution is same as this, then we have proved the fact that our physical assumption, whatever the physical assumption we discussed, will be enough, to make sure that N of t is Poisson process. Okay, for n greater than or equal to 1, we just derive the differential equation for P sub n of t. And the second case is when, what if, this is a very special case, what if n is equal to 0? So that means we don't have no rival. So rival is 0, right? K equal to 0. I mean, n equals 0. No rival during time 0 and t plus delta t. So which means if you split into two intervals, interval 0 to t and t plus delta t, you're not supposed to have any rival in the first interval, and no interval in the no rival in the second interval, right? So we now know the this is the probability that there is no rival in by time t is p sub 0 t by our notation, and we know that this probability over here is given by 1 minus lambda delta t plus the correction factor, right? So you actually arrange all these terms like this, and then divided by delta t on both sides. You have this expression, and this expression goes to derivative of p0 of t when delta t goes 0, right? And also right hand side, actually this one go to 0 when delta t goes 0, so you end up with minus lambda p sub 0 t. So you end up with a very simple differential equation. So when n is equal to 0, when n is equal to 0, so p0 of t will be solved by can be determined by solving this differential equation over here. And when n is greater than or equal to 1, you solve by solving this differential equation, you get the p sub n of t. And solving these differential equations, I like to leave it up to you, and you'll find that the solutions to these two differential equation will be given by this. Okay, the solution to these two differential equations will be like this. And actually this is actually this one coincides with our distribution for the Poisson process, right? This is actually Poisson distribution for this is PDF for the Poisson distribution, probability mass function for Poisson distribution when you have a mean rate of lambda. So that proves our earlier the proposition. Okay. So this is okay. We start from the two physical assumptions and based upon those two assumptions, we were able to end up with the Poisson distribution, the PDF of Poisson distribution like this, and so which implies that as long as the random process N of t is satisfying those two assumptions. What are those assumptions? The first assumption is over the non-overlapping intervals, the number of arrivals will be independent of each other. The increment will be independent of each other. And second assumption is there is no rush hour, right? So rush hour means during very short period of time, delta t, there is only one, there is no arrival, or there is only one arrival, right? No more than one arrivals, right? You're not gonna have two arrivals, three arrivals, or four arrivals, and so on, right? Or you only have gonna have zero or one arrival, okay, over a very small interval of delta t. In fact, the delta t is supposed to be very, very small, right? So as long as these assumptions are satisfied, okay, for n of t, the counting process n of t is supposed, the random process n of t is supposed to be Poisson random process. Okay, this page trying to summarize the definition of Poisson random process, and the counting process, when you have counting process n of t, which is trying to count the number of the event occurring in this interval from time 0 to time t, the n of t is Poisson if these two conditions are satisfied. The first condition is stationary and independent increment, right? So this is actually same as like, you know, this one can be interpreted as the fact that the physical observation that the number of arrivals, okay, during non-overlapping regions will be independent of each other. Um, and the second assumption over here, okay, this is increment, right? This increment that follows the Poisson distribution. So this page actually summarized all the story we just discussed so far. Okay, so far we have looked at arrival process, which has been modeled as for example, Poisson process. In fact, the Poisson process is really good model for arrivals and queuing system. Now, one other important aspect in queuing system is service time. For example, in the bank, okay, customer arrives and then maybe wait for a while and then start getting. If the customer is ahead of line, he or she will be served. Then now question is how long it takes to get his job done. The service times, uh, it takes to complete the service. So what is good model for the service time? If you go back to the Poisson arrivals, we have shown that inter-arrival times will be following the exponential distribution. So exponential distribution is really good model for inter-arrival times. Now, okay, well, think about most of the in your experiences in the bank or post office, or doctor's office, how long does it take to get to complete the service? And mostly, we would say the service demand very brief, very short time most of the time. Okay, most of the time, the the service will be done in very short period of time. Uh, but sometimes, okay, once a while, the service may take very, very long, might take long. Like if you go to the bank, for example, okay, most of people visit the bank and their job might be very, very short, like make a deposit or, paying something. But there's rarely, okay, there is a customer who wants to open up the new account, and okay, opening up the account takes a lot of time, 30 minutes, 40 minutes, something like that, right? So uh, extensive, okay, extensive job is, only rarely occurs. So let's say B of X is service time distribution. Okay, let me use the B of x for the service time distribution, and A of x we use the A of x for the PDF for arrival process, arrivals, inter-arrival time, for example. And B of x, actually, let me use B of x for the PDF for the service time. Okay, so as I said, most of, okay, let me use Z for the service time. Okay, this is service time, random variable to denote the service time, and service time is less than A is actually, if once you have PDF, okay, so this interval, okay, 0 to A, so this area, okay, if you integrated the PDF over 0 to A, okay, that will give you the actual probability that the service is done within time A, right? And if you're gonna find out the service time between C and C plus A, okay, so C and C plus A, so your service time is takes some time between C and C plus A, will be the area in this under the curve, okay. So it's very small. This rarely happens, right? So most of service time is very short. That's what typical experience we have. So this kind of like, this is actually a sort of exponential, right? This is sort of exponential curve, and exponential distribution is a really good model for the service time in general. So in queuing system, a lot of times we model the service time with exponential distribution. So this is the PDF for the exponential PDF for the service time, which is modeled by the exponential distribution like this with the parameter of mu. Actually, 1 over mu is average, right? So average is average service time. Okay, what is the average time you have to spend in the bank to get your job done? Well, by the way, the variance of the exponential distribution is 1 over mu square. Okay, actually, if you square the mean, the variance. Okay, I'm going to discuss some important or interesting property of exponential distribution. Exponential distribution actually will be used as a really good model for service time distribution. Service time. So service time, our service time, a lot of times, okay, we're going to assume that our service time will follow the exponential distribution. And this exponential distribution has a very interesting property called memoryless property. And let me tell you what I mean by the memoryless property. Memoryless means this property that's forgetting, okay, forgetting something, okay, doesn't memorize something. So mathematically, this is what it means. Okay, let Z be Z denoted the service time, a random variable to denote the service time, and okay. Let me draw the timeline. You have time 0 and you have the time T0 and T1. And okay, your service starts here. Okay, your service starts at time 0, and then you have been served until time T0. Okay, Z has been Z, so you are being okay. So until time T0, service is not completed, right? So service is going on. So still service is going on. Service is going on. Okay, and your service will be completed sometime between T0 and T1, right? So service time will be less than T1, which means service will be completed before T1. But service is going on until T0, okay, which means service will be done, okay, here. Service to be completed. So you're interested in the probability that service will be completed until time T1. Okay, and what this property says is, Okay, your service starts immediately. I mean, your service starts at time t0, and then the service will be completed by t1 minus t0. Okay, this is t1 minus t0. So this is actually service to be completed, okay, before t1 minus t0. And we're saying that these two probability, okay, these two probability are equal to each other. That means, okay, actually the service time doesn't care how long you've been served. Okay, well, the first case over here, so you've been served, the service has not been completed by time t0. So you have some more time to go until it's completed, right? But if you start counting here, okay, starting from t0 here, okay, no matter how long I have been actually in service, okay, service time to be completed will be same, right? Okay, actually it doesn't care I've been served for a long time. Okay, so that implies that, okay, even if I've been served for a long time, there is no lush service. There's no lush service for, even if I've been served for a long time, right? Because my service time over here, okay, my service time over here will depends on t1 minus t2 only, right? It's same as actually starting from the time t0. Okay, so it doesn't memorize, it doesn't care, okay, how long I have been served. Okay, the service time to be completed will not depend on how long I have been served so far. That's what I mean by the memories property. I can give you a good example here. If well, this is what it is. Okay, let's say z is let me use the z to denote the lifespan. Okay, actually lifespan is same as actually my age, right? Okay, random variable. So like my age is 56 right now, and let's say there's 70 here. Okay, and this is an assumption. Okay, the probability that actually I survive until 70 years old, assuming that actually I've been living, okay, more than 56 years. Actually, so currently, okay, my lifespan, lifespan is more than 56 because I'm survived by now, okay. But I still, okay, want to find out, okay, how long I can survive until 70 years old. That probability, okay, if the z has memories property, then this probability is the same as actually z is less than t1 minus t2 actually, which is 70 minus 56, that's 14, right? So what it means is actually the probability that I survive until 70 years is same as the probability that the newly born baby, okay, actually there's no condition, right? So lifespan for the newly born baby is survive until 14 years old. So like I have another timeline here. Okay, there's 0. Okay, newborn baby, okay, there is let's say 14 years. Okay, so the probability that this newborn baby survive until 14 years old, okay, is same as probability that actually I survive for next 14 years. Okay, is this true? In practice, is it true? Okay, I've been living 56 years. I've been survived 56 years, and then I'm looking for the probability that I survive 40 more years, right? Until like I'm 7 years old. So 14 years. Okay, this probability is same as actually probability that newborn baby, okay, survive for 14 years. Okay, and the probability is both same. That's what the memories property says, right? Is the memories property realistic? Well, in this case, okay, in this particular example, I don't think this is realistic, right? because the probability that newborn babies survive more than 14 years will be actually much larger than I survive for next 14 years, right? Because I have condition here. I lived long enough. Actually, I lived for 56 years old. Okay, 56 years. So um, so since now I'm very old, and the probability that I survive more than 14 years from now on will be much. It has this probability is much less than probability that newborn babies survive for next 14 years. But even if this, okay, well sometimes this kind of like if I model, okay, if I model the lifespan with exponential distribution, then it's not realistic because it has memoryless property. But in queuing system, okay, still like the if we use the exponential distribution for service time, um, well, I told you that it's really good model, and it has this interesting or some strange property. And the next thing we have to do is we have to prove this. We have to prove that exponential distribution has memoryless property. And the way you have to prove is to show these two probabilities are equal to each other. So in this page, I'm trying to follow that, trying to prove that the exponential distribution has the memoryless property, and all you have to show is this probability over here is okay. You just follow the lines, and you end up with this, and this is probability that actually z is actually t0 and so z is between t0 and t1. Okay, this is same as this. Okay, so these lines will show to prove the position.